Imagine a helicopter at rest, its blades still like slumbering giants. These blades, seemingly inert, hold within them the potential for incredible power and agility. These blades, often crafted from lightweight yet robust materials like aluminum or composites, are designed to be flexible. This flexibility is not just a design choice but a necessity for their function. This inherent flexibility is crucial for their performance in the air. It allows the blades to withstand the immense forces they encounter during flight. When the helicopter roars to life and the rotor spins, a remarkable transformation occurs. The blades, once dormant, begin to move with purpose and precision. The once dormant blades come alive, slicing through the air with incredible force. They generate the lift needed to overcome gravity and propel the helicopter into the sky. As the rotor spins faster, the blades begin to lift due to the aerodynamic lift generated. This lift is a result of the air pressure differences created by the blade's motion. This lift force acts perpendicular to the surface of the blade, pulling it upwards. It's a delicate balance of forces that keeps the helicopter aloft. However, the blades don't simply lift straight up. They follow a complex path influenced by various aerodynamic factors. Instead, they rise and assume a cone-like shape, a phenomenon aptly named coning. This shape is a visual representation of the forces at play. This coning effect is a direct result of the interplay between several forces acting on the rotating blades. These forces include lift, centrifugal force, and aerodynamic drag. Understanding coning is not just an academic exercise, it's fundamental to grasping the principles of helicopter flight. Pilots and engineers must consider these dynamics to ensure safe and efficient operation. In the following sections, we will delve deeper into the forces at play and the factors that influence this fascinating phenomenon. Stay tuned as we explore the intricacies of helicopter blade dynamics and their impact on flight. To comprehend coning, we must first understand the two primary forces engaged in a delicate balancing act: centrifugal force and aerodynamic force. These forces are crucial in determining the behavior and performance of helicopter rotor blades during flight. As the rotor spins, the blades experience an outward force, much like a ball on a string being swung in a circle. This outward force is essential for maintaining the structural integrity of the rotor blades. This is centrifugal force pulling the blades away from the rotor hub. It acts along the length of the blade, trying to straighten it out and keep it extended. Simultaneously, aerodynamic force comes into play as the spinning blades cut through the air. This force is generated by the airflow over the blade surfaces. This force, perpendicular to the blade's surface, provides lift, counteracting the weight of the helicopter and pushing the blades upwards. The balance between these forces is what allows the helicopter to hover and maneuver effectively. The faster the blades spin, the stronger the lift generated. This increased lift is crucial for the helicopter to ascend and maintain altitude. The degree of coning is a direct consequence of the equilibrium, or lack thereof, between these two forces. Coning is a visible indicator of how well these forces are balanced. If centrifugal force dominates, the blades will rise higher, resulting in excessive coning. This can affect the helicopter's stability and control. Conversely, if aerodynamic lift is insufficient, the blades will droop lower, potentially leading to dangerous situations. Ensuring the right balance between these forces is critical for safe and efficient helicopter operation. The angle of the cone formed by the rotating blades, known as the coning angle, is not constant. This angle is crucial for understanding the dynamics of helicopter flight. It fluctuates based on several key factors, each playing a significant role in the overall performance and stability of the helicopter. First, rotor RPM, or revolutions per minute. This is a measure of how fast the rotor blades are spinning. Higher RPM translates to greater centrifugal force, pushing the blades outwards and increasing the coning angle. This is because the faster the blades spin, the more they are pulled away from the center. Conversely, lower RPM reduces centrifugal force, leading to a smaller coning angle. Second, gross weight. The weight of the helicopter, including its cargo and passengers, affects the coning angle. A heavily laden helicopter will experience greater downward force due to gravity. This increased weight requires the rotor blades to work harder to generate the necessary lift. To counteract this and maintain lift, the blades need to generate more lift, which in turn increases the coning angle. And finally, G-force. This is the force of gravity or acceleration acting on the helicopter. Maneuvers involving high G-forces, such as sharp turns or rapid acceleration, also impact coning. These maneuvers temporarily increase the effective weight of the helicopter. Requiring more lift and consequently, a larger coning angle. The pilot must be skilled in managing these forces to ensure a smooth and safe flight. Pilots are acutely aware of these factors and constantly adjust the helicopter's controls, such as collective pitch and cyclic pitch, to manage the coning angle and maintain stable flight. This continuous adjustment is essential for the safety and efficiency of helicopter operations. While some coning is necessary for helicopter flight, excessive coning poses significant dangers. As the coning angle increases beyond a certain point, the effectiveness of the blades in generating lift diminishes. This reduction in lift can cause the helicopter to lose altitude, a situation pilots strive to avoid. Another danger lies in the structural limitations of the blades themselves. Excessive coning places immense stress on the blades, particularly at the root where they attach to the rotor hub. In extreme cases, this stress can lead to blade flapping, a phenomenon where the blades flex excessively upwards and downwards. Blade flapping can cause vibrations throughout the helicopter, reducing controllability and potentially leading to catastrophic blade failure. Section 5. Coning versus bending stress. Two different beasts. It's crucial to distinguish coning from another stress experienced by helicopter blades, bending stress. While both are related to the forces acting on the blades, they are distinct phenomena. Coning, as we've discussed, refers to the overall upward tilt of the blades, forming a cone shape. Bending stress, on the other hand, refers to the localized stresses within the blade structure itself. As the blades rotate, they are subjected to varying aerodynamic forces along their length. These forces can cause the blades to bend and flex, particularly during maneuvers or turbulent conditions. Helicopter designers employ sophisticated materials and construction techniques to manage both coning and bending stresses. The blades are carefully engineered to withstand the immense forces they encounter, ensuring safe and reliable operation. Section 6. Engineering Solutions. The Brilliance of Pre-coned Blades. To mitigate the challenges posed by coning and optimize blade performance, engineers have developed ingenious solutions, one of which is the concept of pre-coned blades. Unlike traditional blades that are initially straight, pre-coned blades are manufactured with a slight upward angle built in. This pre-existing angle helps distribute stress more evenly across the blade during rotation, effectively reducing the amount of coning that occurs in flight. Pre-coning offers several advantages. It reduces the stress on the blades, particularly at the root, enhancing their lifespan and reliability. Additionally, it improves the helicopter's handling characteristics by making the control response more predictable. By predefining a portion of the coning angle, pre-coned blades contribute to a smoother and more stable flight experience. Section 7. Iconic examples: helicopters designed with pre-coning in mind. The Bell UH-1 Iroquois, more affectionately known as the Huey, stands as a prime example of a helicopter employing pre-coned blades. This iconic aircraft, renowned for its service during the Vietnam War, utilizes pre-coning to manage the stresses on its blades and ensure reliable performance in demanding conditions. Another notable example is the Boeing AH-64 Apache, a formidable attack helicopter known for its agility and firepower. The Apache's blades are also pre-coned, allowing it to withstand the stresses of high-speed maneuvers and combat operations. These examples highlight the importance of pre-coning as a design consideration in helicopters, particularly those operating in demanding environments or performing maneuvers that subject the blades to high stresses. Section 8. The importance of understanding coning for safe flight. Understanding coning is not just a matter of academic curiosity, it's fundamentally important for ensuring safe helicopter operation. Pilots undergo rigorous training to recognize and manage the factors that influence coning. They learn to anticipate how changes in RPM, weight, and G-force will affect the coning angle and adjust the helicopter's controls accordingly. By carefully monitoring and controlling coning, pilots can prevent dangerous situations like excessive coning or blade flapping. They can maintain stable flight, even in challenging conditions, ensuring the safety of themselves, their crew, and anyone on the ground below. Section 9. Conclusion. A Symphony of Forces in the Sky. Helicopter flight is a delicate interplay of forces, a symphony of lift, drag, thrust, and weight. Coning, a phenomenon often unseen by the casual observer, plays a critical role in this intricate dance. By understanding the forces involved, the factors influencing coning and the potential dangers of excessive coning, we gain a deeper appreciation for the complexity and ingenuity of helicopter design. From the flexible blades to the sophisticated control systems, every aspect of a helicopter is engineered to manage these forces and ensure safe and controlled flight. So, the next time you see a helicopter soaring overhead, take a moment to appreciate the invisible forces at work, silently shaping the cone of its rotor disc and enabling these remarkable machines to defy gravity.